Hello and welcome to this video where I want to recap the lesson that we have just had a few moments ago, and this one will assist you in going through the assignment which I've already sent in your Google Classroom. We looked at a number of questions, and when we were discussing, especially towards the end, I realized that majority of you were not in the previous class. So this is what I would recommend. I'd like you to go back to the Google Classroom, look for the video which I recorded on waves. Then after studying that, continue with this one, because here I just want to recap the business of today's lecture, where I mainly took you through problem solving in waves. So I want to go through this first question here so that at least you can be able to see how we solved it. And because this one is just a recap, I'll go straight to how it is worked out. Okay, first of all, I reminded you about this type of graph. A displacement. My handwriting is not so good right now. I reminded you about a displacement distance graph. Displacement has got the units meters and the distance has got the units meters. So when we draw a graph, a wave like that, from here to here, it will be a complete oscillation. And the physical quantity I get along the x-axis, which has got the units meters, must be the distance covered by the wave when the wave makes one complete oscillation, and that distance must be equal to wavelength. Another complete oscillation is from a crest to the next crest, adjacent crests. The distance between two adjacent crests is also a wavelength. The distance between a trough and the next one, let me just add a wave there. There's a trough there, there's this other trough here. Again, this is the wavelength. So there are several ways in which you can get the wavelength from a displacement distance graph. The other type of graph is a displacement time graph. Displacement again S. And here we have time in, let's say, units seconds. So if I have, for example, a wave like this, and by the way, from both graphs, this distance here represents the amplitude. Even on the displacement time graph, this distance here will represent the amplitude. So a complete oscillation again is from this point to this point. So the physical quantity represented by this space here, from this point to this point, is the time, because time is on the axis. It is a time taken by the wave to make one complete oscillation, and that is periodic time. Again, I can get the periodic time from here. This will give me the periodic time. Another way of getting the periodic time is here. And of course, don't forget that you can also get the periodic time from, I've already talked about the neutral point and the neutral point here. Again, from the neutral point to the next neutral point there. That again gives me the periodic time. So I would have liked to review that. Another point that I would like to review in this lecture is the physical quantity speed, which is distance divided by time. And I say that if distance is given, time is given, you can use those physical quantities to calculate the speed. But you can also calculate the speed of the wave if you consider the distance that the wave covers when it makes one oscillation, and that distance happens to be wavelength, divided by the time taken by the wave to make one complete oscillation. So notice that the distance is that covered by the wave when it makes one oscillation. The time is the time taken by the wave when it makes one complete oscillation, and we call it periodic time. So if I divide this by this, I will get the speed of the wave. And then, of course, this one translates into lambda times 1 over t. And somewhere during this particular lesson, I told you 1 over t is actually frequency. So this one is going to be equal to lambda times frequency. So there are 3 equations that you can use to calculate. Actually, yeah, 3 equations. Distance over time will give you speed, or lambda over t, or lambda f. Now let's go to this particular equation. We are told that waves on a spring are produced at the rate of 20 wavelengths every 5 seconds. So, one wavelength, you can see one wavelength corresponds to one complete oscillation or one cycle. So I can say this wave makes in 5 seconds. This system makes 20 cycles or 20 oscillations. Let me make the pen less thick, something like that. So frequency is the number of cycles made in unit time. So in 1 second, how many cycles are we going to have? And you can find that I'm going to have 20 times 1 divided by 5, and I get 4 oscillations. Just the short form of oscillations. So in 1 second, the system makes 4 oscillations. So the frequency is the number of oscillations made in 1 second. So it follows that the frequency is 4. What are the units of frequency? Hertz, or per second, or seconds raised to minus 1. Any number, like for example, if I say 1 over x, it can be expressed as x raised to minus 1. That is what this means. Okay, let's go on to the next part. If the wavelength of the wave is 0.01 meters, find the speed of the wave. So I want v, speed of the wave. And now let's look at the number of physical quantities I have. I have frequency and I have wavelength. See, this one here is wavelength. If I have frequency and wavelength, I just look for the appropriate equation, which is this one here. So I'm going to get wavelength times the frequency. The wavelength is 0.01 meters times 4 per second. And this one will give me 0.04 meters per second. As simple as that. Let's see how we get the periodic time. Again, looking at this, you can see periodic time is given as if 1 over f is equal to, 1 over t is equal to f, then it follows, if I cross multiply, I can find that 1 over f is equals to t. And that is what I'm going to use. T is going to be equal to 1 over f. The f is 4. Therefore, the periodic time is 0.25 seconds. And that question is just solved that easily. Let's go to the next question. So this is question number 4. We are told that a water wave travels 12 meters in 4 seconds. So I've got the distance. This is the distance, and this is time. So as soon as I realize that, and I remember speed is equals to distance over time, immediately I know what physical quantity I can be able to calculate from here. But let's go on. If the frequency is so much, this is frequency. Calculate the speed of the wave. Of course, we have just seen that the best way to do is to divide the distance by the time. The distance being 12 meters, time being 4 seconds, and this will be 3 meters per second. 3 meters per second. As simple as that. Wavelength. Wavelength can be obtained from here. Notice that how knowing the equations which are there can help us. So over here, I can be able, what is it that I need to do in order to get wavelength? I divide both sides by f because I don't need f. F cancels here, and I can see wavelength will be equal to speed divided by frequency. Speed divided by frequency. The speed is 3 meters per second. The frequency is 2 Hz or 2 per second. Again, you can see how the units cancel out so well, like that, giving me an answer of 1.5 meters. 1.5 meters. Very easy. Let's go to the next one. So the last question was question number 5. In question number 5, I'd like to make a correction because when I was teaching you, I was using the distances given here in meters because somehow I did not see these centimeters here. So I'm going to give the answers to this question with that correction in mind. Actually, one of you corrected me, and I'm very grateful for that. That shows that you're very alert when you are taking my lectures, and continue with that good habit. So let's read the question. The figure 8.9 shows a snapshot of a wave formed in a string. The waves in the diagram show the scale in centimeters. The speed of the wave is this. So already here we've got speed. Again, remember the equations. Speed is distance over time is equals to wavelength over periodic time is equals to wavelength times f. Very easy. Periodic time is equals to the inverse of the frequency, or frequency is equals to the inverse of the periodic time. And of course, don't forget those displacement distance graph, what they represent. A displacement distance graph, what the quantities on the x-axis for one complete oscillation represents, because that is what you will need here. Notice that this being a snapshot, the quantity on the y-axis must be displacement in centimeters, and the quantity on the x-axis must be distance, again in centimeters. That is the correction that I wanted to make here. So with the reference to this waveform, determine the wavelength. And you will agree with me, the wavelength is either from this trough to the next trough, this one here, which will be from 0 to 40, which is 40 centimeters. This must be the wavelength, or from one crest to the next. This must also be the wavelength, which is 60 minus 20, because from here to here is 20 and from here to here is 60. So again, I get 40 centimeters. And if you wanted to use the neutral point from 10 all the way to 50, again 50 minus 10, you get this being the wavelength. So there are several ways of getting the wavelength. Okay, 50 minus 10, again 40 centimeters. So the wavelength is 40 centimeters. So this one does not matter how you worked it out. Convert that into meters. The reason why I do that is because I can see the speed is given in meters per second. So I want to get the wavelength to be in meters, meters, like that. Amplitude. It's even easy. Amplitude is the maximum displacement of the particle from here to here, which it means this is 5 centimeters. Let's look at the frequency. We want the frequency. What do we have? We've got wavelength and V. Wavelength and V. So that means the frequency must be the speed must over the wavelength. The speed is 10 meters per second and the wavelength is 0.4 meters. And this will be like, let me just get an accurate value for that. So that is 10 divided by 0.4 4, and I get 25. 25 has. 25 has, or 25 per second. The period. Look at how these questions are. They are very simple. It is 1 over frequency. And how am I getting this? Is because I have this information in mind. Very important. Very important. So 1 over 25. Let me do 1 divided by 25. I get 0.04. 0.04 seconds. That should be it. And that is how we worked out those questions. So go through this video again and again and again and again, and then go through the assignment which I've posted in the Google Classroom.